who will talk about causal influence in quantum theory. So, Jonathan, the floor is yours.
Thank you very much. Thanks to the organizers and thanks for the invitation and all that. A great shame I can't be there. It looks very nice. So yes, causal influence in quantum theory is what I'll be talking about. So there is by now a large literature on classical causal models, and there's increasing interest in that literature from other communities, lots of machine learning and AI sorts of people talking about it these days, and an increasingly broad array of applications, whether it be automated medical diagnosis or whatever. But this literature also raises or perhaps casts new light on more foundational questions, such as if A is a cause of B, then what sort of thing are A and B? What does it mean to say that A is a direct cause of B? Do causal concepts involve in an essential way interventions by agents? Are causal relations directed in time? And what in the overall picture is ontic, i.e. factual and independent of any agent? And what is epistemic, i.e. relative to an agent's knowledge or beliefs? Now, of course, there's quite a literature addressing all of those kinds of questions. A lot of it is done just in the classical case, just assuming our sort of everyday world of classical things and perhaps with classical causal models in mind. But of course, the classical world really is emergent out of the quantum world. Physical systems in our world actually obey the laws of quantum theory. So any full account that answers these kinds of questions should really start with quantum theory. And what I'm going to do is provide an account of causal relations in quantum theory that you can see as answering some of these questions in fully quantum terms. Several things will come out of this. One is a quantum notion of causal model that generalizes the sort of traditional classical definition of a causal model, from which classical causal models are then obtained as a special case, essentially when quantum operators are all diagonal. Another thing that will come out, which I will get to if there's time, we'll see what happens, is some much more speculative ideas concerning new directions in the interpretation of quantum theory. So the talk is structured something like this. I'll start off talking about causal influence versus the concept of signaling. The idea of that discussion is that it will motivate studying unitary transformations in particular. And so I'll go on to discuss causal influence through unitary transformations, then causal influence in unitary processes, which are built up of lots of unitary transformations. Then I'll come on to something I'll call causally faithful circuit decompositions, and I'll explain what that means at the time. And as I said, depending on how much time left at the end, speculative remarks about interpretation of quantum theory. So let's, oh yes, and I'm assuming finite dimensional systems throughout, and really haven't thought that much about possible generalizations to infinite dimensional systems. So I'm just assuming finite dimensions for now. So let's talk about causal influence and also signaling. And we're going to start just with something classical. So I'm considering here a classical function that I've represented in a sort of circuit notation as a gate. The gate corresponds to a function f, and it has two inputs, x and lambda, which in this example are going to be classical bits, and it's got one output, z, which is also a classical bit. And we're going to suppose that z is simply the parity of x and lambda, that is z equals x plus lambda mod 2. Okay, and suppose that lambda is somehow hidden, and that from some agent's point of view, they give a probability to lambda being 0 and a probability to lambda being 1. And let's suppose that those probabilities are a half each. Well, then we can talk about the marginal channel from x to z, the channel that we get by marginalizing over lambda. Well, in that channel, the output z is completely random, of course, and independent of x. So what this means is that from the point of view of an agent who doesn't know the value of lambda and assigns those probabilities, there is no signaling from X to Z. Someone, if that agent is deliberately intervening on X, fixing it to be 0 or 1, then the value of Z is independent of that. But what we should say here is that independently of any agent, there is causal influence from X to Z. Because once you see the full picture with the lambda there as well, you see that in the function f, Z does indeed depend on the value of X. It depends on both X and lambda. So this is an instance of what's often called fine tuning. We do indeed have causal influence from X to Z. But when we marginalize over lambda, we don't see signaling. But this only happens for that very particular distribution on lambda, half-half. For other distributions on lambda, you would still see signaling from X to Z. We can describe a very similar example in the quantum case. So here, again, I've got a small circuit. This is a C0 gate. It's got 2 qubits as its input, A and lambda, that controls on A. I put a little symbol on B there, which indicates that we're just tracing out B. We're not going to be interested in that one. And the other output is C. Now, suppose that what's happening is that someone tosses a coin and then prepares the 0 state of lambda if it's heads and the 1 state if it's tails. Well, then let's assume a fair coin. To an agent unaware of the value of the outcome of that coin toss, they'll assign a state to lambda, which is a mixed state ion 2. And then you can marginalize over that lambda system and look at the resulting channel from A to C. And from that agent's perspective, there's no signaling from A to C. And this is an instance of fine tuning again, because with other values of rho lambda, you would see signaling from A to C. And again, there clearly is causal influence here from A to C. Indeed, from another agent's perspective who knows the value of the coin toss, a signal can indeed be sent. So what do we take away from this brief discussion? Well, we should conclude in both classical and quantum cases that causal influence should not be defined by signaling. And signaling is an epistemic notion. So whether Alice can signal to Bob depends on what both of them know, or even in more general examples on things like what Alice knows about what Bob knows, and so on. So let's ask the question, in a quantum universe, what then is a good notion of causal influence, distinct from just the idea of signaling through a general channel? And I'm going to argue as follows. Although fine-tuned unobserved systems can result in an absence of apparent signaling, causal influence can be defined once all relevant systems are included in the description. So that happened in the classical case. Once we included lambda and saw the function f as a function of both the other input and lambda, then we saw that the output was influenced by the other input, and similarly for the quantum example with the C0. Now, when all relevant systems are included in the description, we're now dealing with a closed system, and at least in standard quantum theory, closed systems evolve unitarily. I'm not going to deal with more speculative ideas wherein the fundamental quantum evolution is some kind of CP map rather than a unitary. I'm just sticking to standard quantum theory here, where closed systems do evolve unitarily. And so what we get out of this argumentation is that causal influence should be defined in terms of unitary transformations. Okay, so let's do that. This is just some notation on this slide. So consider a quantum channel with input A and output B corresponding to some trace-preserving CP map E. Then the state at the output rho B could be written as the CP map E applied to the input state rho A. And that CP map will have a Choi-Jamelkowski isomorphic operator, which I'll take to be given by an expression like this. There can be different conventions here. So in a way, I'm showing you what conventions I'm using. A star is the dual space to A. And the reason for choosing these particular conventions is that this way, the operator, which I write as rho with a subscript, b given a, is a positive operator. And if we trace out the B system on that operator, we just get the identity acting on A star. Okay, so I'll be writing operators like this sometimes, representing channels, some rho and then output of the channel given input of the channel. Okay, and now we'll make a definition of causal influence through a unitary transformation. So we consider a generic bipartite unitary transformation U with inputs A, B and outputs C, D. Well, we'll say that A does not influence D if the following condition holds. For all inputs rho B, if I trace out C and just look at the marginal state on D at the output, then that marginal is independent of rho A. There are actually a whole slew of different definitions that you could make here, but they're all equivalent, is the nice thing. So here's one of them. Equivalently, if I consider the Choi-Jamelkowski operator for that unitary and trace out C, then it ends up having a certain form, which is the operator rho CD given AB with C traced just turns into rho of D given B, where that's some channel from B to D tensored with identity on A. This is related to signaling, of course, this definition. Another way of saying it is that if you trace out C, then roughly there's no signaling from A to D. But importantly, that's asserted not just for a particular input at the state B, but there's a quantification, it's for all states on the input B, there is no signaling from A to D. So that is another equivalent way of stating it. But I wouldn't necessarily want to take that way of stating it as the most fundamental, because it appeals to signaling, which is bound up with agents and things. And the way I see the story that I'm telling here, it's not necessarily one that takes things like agents and signaling and things that agents do to be fundamental here. Okay, and a little more notation. So if A in fact does influence D, then we will sometimes write it this way, A with just a sort of double arrow into D. And if A does not influence D, A with the arrow crossed out into D. All right. And now I'm going to state a theorem about unitary transformations. And I'm calling this the Uber theorem because most of the rest of what I'm going to say follows from this theorem in one way or another. Some of the things I'll say follow immediately from this theorem, and some not immediately, but with a bit of further work. But nonetheless follow from it in some way. So the Uber theorem is this. Let's consider some unitary transformation with inputs A1, A2 up to AK, and outputs B1, B2 up to Bn. For each of those outputs, I can define the subset of inputs which do influence it. And I'll call those inputs the parents of that particular output. So let PA subscript I then be the set of parents for the output BI. So that is, it's a set of inputs AJ such that AJ does influence the output BI. And here's then the statement of the theorem. If we write down the Choi-Jamelkowski operator for that unitary transformation, here it is. So that's rho for the unitary transformation U, outputs B1 to Bn given inputs A1 to AK. That Choi-Jamelkowski operator takes a certain special form, which it's a product of operators, one for each output Bi, and where each of those terms is a channel It's the Choi-Jamalkowski operator for some channel from the parents of that output bi into bi, where furthermore all of those terms commute. So in the product, it doesn't matter which order I write them in. Okay, well, I'm not going to prove that now, but it's true, and we're going to use this to do things. A little convention here. Quite often I write down a product of operators that appear to act on different Hilbert spaces, and people might then wonder, well, how is it even defined? The idea is you sort of pad with tensor products with identities anytime you need to in order to make products of operators well defined. Okay, so I'll say straight away a couple of consequences of this Uber theorem. One is a thing that I'm calling causal atomicity, which is the following statement. If I have this unitary transformation, suppose that one of the inputs, AI, does not influence one of the outputs, Bj, and also that same input, AI, does not influence another one of the outputs, Bk. Well, if I combine B and J and Bk together and regard them as a composite system, just one system on its own, then it also follows that AI does not influence that composite system, Bj, Bk. So this is essentially immediate, I think, given the Uber theorem. Note that this is true for unitary channels. And if we were discussing classical functions, we could also discuss causal influence through a classical function. And then trivially, this same statement would be true. Yeah, if a given input X is not influencing output Y through a function and not Z either, then pretty trivially, it's not influencing the classical variable defined as the pair of Y and Z. However, a statement like this is not true in general if we're discussing signaling through a CP map, or in the classical case, a general stochastic map. So in that case, it can very well happen that an input doesn't influence some output, and not another one either, but does influence the pair. I mean, just think of an input being a classical bit. You can have its value written into the parity of two of the outputs, which are both locally random, for instance, in which case it's not signaling to either of them on their own. So something follows from this causal atomicity, which is that there's a certain simplicity to the causal structure of a unitary transformation, because that causal structure can be completely specified by those parental sets. We just need to consider each output on its own and specify its parents amongst the inputs. And once I've done that, I've completely specified the causal structure of a unitary, which means graphically something nice. I can draw that causal structure just by drawing arrows from inputs, individual inputs to individual outputs. I'll draw an arrow whenever an input does, in fact, influence a particular output. For general CP maps or classical stochastic maps, this wouldn't be true, and I couldn't represent the causal structure just by drawing simple arrows in this way. I'd have to have a much more complicated picture where I think about arbitrary subsets of the inputs and arbitrary subsets of the outputs. Okay, here's another consequence of that Uber theorem thing. This I'll call causal reversibility. So if I consider a particular unitary transformation, that one with inputs A1 to AK and outputs B1 to Bn, I can draw its causal structure with these arrows. Well, to get the causal structure of the inverse unitary U minus 1, I just flip the arrows. So here's the inverse U minus 1. It has inputs, we're reading top to bottom now, so it has inputs B1 to Bn and outputs A1 to AK. And to get its causal structure, I just draw the causal structure of U, which is here, and flip those arrows. Now, in case anyone thought that was obvious, it's not so obvious, and it's actually stronger than the mere claim that unitaries are reversible transformations. In fact, it's not true for classical functions. It's not even true for classical reversible functions. The classical C0 gate is an example of a classical reversible function, which is actually a counterexample there. So it's more special than just the claim that unitaries are reversible transformations. Something similar does hold if we're not considering all classical reversible functions, but rather classical symplectic transformations on phase spaces. So you do get a similar kind of claim if it's classical mechanics that you're thinking about. Okay, now let's turn to consider quantum processes rather than just a single unitary transformation. So here's an example of a process. It's got some initial inputs, lambda 1 to k, and outputs mu1 to mu(n). And it's a process consisting of a bunch of unitary transformations. I've drawn this for the general case. Not every unitary transformation has to act on all systems. This would look a bit more like a sort of conventional quantum circuit if U1, for instance, was only acting on a couple of the systems and U2 only on a different couple of systems and so on. So I'm just being general by allowing each of these unitary transformations to act on all systems. They don't have to. Now we're going to break some of the wires. You can see I've done that in the picture, and I've labeled those breaks A, B, C, and D. So what does a broken wire correspond to? Well, I'll call it a quantum node. And the idea is that we think of one of these quantum nodes as a kind of locus within the process at which we can consider an additional possible evolution of the system. So I don't want to emphasize the role of agents here too much for reasons I said earlier, but sometimes pedagogically it's kind of helpful to mention them. So if you like, you can think of an agent stationed at that point in the circuit, and that agent is able at that point to do an intervention on the system, a measurement or an extra little unitary transformation if they want to. So one of these loci will be associated with two Hilbert spaces, one with the bottom part of the broken wire and one with the top part. So for the node A, for example, I'll label these HA in and HA out. And the most general thing an agent could do there would be described by a quantum instrument that then mediates this incoming Hilbert space and the outgoing Hilbert space. And the whole thing here is an example of something that's been studied quite a bit in the literature under different sorts of names. Sometimes these are called supermaps, sometimes quantum cones, amongst other things. So what I want to do is define a causal structure for these quantum nodes. And in order to do that, we don't have to do very much. We just stretch the wires. So if we look at what was the A node here, you can see that the outgoing wire, the top part of the broken wire associated with the A node, has sort of been stretched down to the bottom of the diagram and is still labeled with A out. And the incoming wire for that A node has been stretched right up to the top of the diagram and is still labeled with A in. And same for B, C, and D here. And the reason for doing this is that when you do that with your picture, you see that the overall unitary process can be thought of this way. It actually corresponds to, in fact, is identical with just one big unitary transformation V, whose inputs are all the things that were at the bottom here. So A out, B out, C out, and so on, and whose outputs are all the things at the top here. So it's A in, B in, and so on, along with the mu's. And now we can define direct cause relations in our process by appealing to the definition we already have for a unitary and applying it to V. So we're going to say that in this process, a node X, where in the example X might be any of A, B, C, D, or one of the initial inputs, lambda I, we'll say that that node X is a direct cause of another node Y, if and only if X out influences Y in this unitary transformation V. And some things then follow from the causal atomicity I was talking about. That's the thing that ensured that if you just have one unitary transformation, you can represent its causal structure with arrows from inputs to outputs. From that, it follows that the causal relations in this whole process can be represented by a directed acyclic graph. And it's important to understand that that follows from causal atomicity. It's not completely trivial that a directed acyclic graph is the right mathematical object for representing causal relations here. But it does follow. Otherwise, you might have just been thinking about a partial order, something weaker like that. But actually, they're represented by a directed acyclic graph. And there's this neat thing of causal symmetry, which shows that the causal structure of the inverse process is given by flipping the arrows. Okay. From the Uber theorem, it follows that the operator sigma representing the supermap can now be written as a product of commuting channels, where in that product, we have a channel for each node that appears in the DAG, and it's a channel from the parents of that node in the DAG into the input space for that node. And all of those channels commute. All right, I'm going to skip that bit and come on to the idea of causally faithful circuit decompositions. Can I ask, how much longer have I got?
Yes, you have 15 minutes.
Okay, okay. So here's what this next bit is going to be about. The commutation of the operators in the Uber theorem induces tensor factor and direct sum decompositions of the Hilbert spaces in interesting and intricate ways. And the reason I want to show you this bit is that it's really here, I think, that we see what causal relations in quantum theory are all about. And the structure of causal relations in quantum theory is really to do with these tensor factor and direct sum decompositions of Hilbert spaces. I'm going to explain what I mean by starting with a couple of quite simple examples. So let's consider again just a bipartite unitary transformation. It'll have inputs A1 and A2 and outputs B1 and B2. And let's suppose that for this unitary transformation, it happens that A1 does not influence B2, and also A2 does not influence B1. Well, then something follows actually immediately from that Uber theorem, which is that this unitary transformation can be written as a direct product of two unitary transformations, V and W, where V is just a unitary transformation from A1 to B1 and W from A2 to B2. And the nice thing about writing the picture that way is that it makes the causal structure explicit in the diagram. So once you've written it this way, it's obvious that A1 doesn't influence B2 just because there's no path from A1 to B2 through this circuit. Let's look at another example. Let's consider a tripartite unitary now. It's got inputs A1, A2, A3, and outputs B1, B2, B3. And we're going to suppose that A1 does not influence B3 here, and A3 does not influence B1. So actually A2 is the only thing that does influence both of B1 and B3. So it's playing the role of a sort of complete common cause here for B1 and B3. So we're going to ask a similar question. Can the causal structure of this unitary be made evident by decomposing you into a circuit? Well, if it could, then the circuit would have to look like this one here, with unitary transformations S, V, W, and T. So you can see that this circuit does have the right structure. It's evident that A1 does not influence B3 because there's no path from A1 to B3 through this circuit, and similarly from A3 to B1. But the answer to our question is no, unfortunately. At least some specific unitaries might admit a circuit like that, but not in general. However, we can do something else. It turns out that any unitary with these indicated no influence conditions can be written with a kind of extended circuit diagram that looks like this. you'll see it looks a bit like a normal quantum circuit, but it's got these indices appearing, this index I that appears on some of the wires and also the gates. These gates are still unitary transformations. And in this picture, it's again the case that there's no path from A1 to B3. So that's nice because it makes explicit that A1 cannot influence B3. So what do these indices mean? Well, in a conventional circuit diagram, each wire corresponds to a Hilbert space. And if I have two parallel wires, they correspond to the tensor product of the two Hilbert spaces. The way this diagram works is that these two wires in parallel, which have both got I on them, correspond to a direct sum indexed by I, where each term in the direct sum is a tensor product of two Hilbert spaces. And so if we look at the slice corresponding to this red dotted line, that slice corresponds to an overall Hilbert space, which is HA1, that's just the Hilbert space corresponding to the A1 wire that doesn't have an index. Tensor, the thing corresponding to these two parallel wires with I's on them, which is going to be isomorphic to the Hilbert space HA2. And has the structure that I described. And then tensor another Hilbert space for this wire A3. Okay. And the point here is that a theorem says that any unitary with these no influence conditions can be decomposed into a circuit, an extended circuit, represented by a diagram like this. And this idea generalizes. So here's just a bit of a fancier example. This is a unitary transformation with 4 inputs and 4 outputs. This sort of little thing on the left is supposed to indicate the causal relations. So there's an output B2, whose parents are just A1 and A3, and B2 is not influenced by A2 or A4. That's why B2 is in red here, and there's a red oval around A1 and A3 here. Similarly, output B1 is not influenced by A4, but is influenced by the other 3, and so on. So that's how this picture on the left summarizes the causal relations. And then the claim is that any unitary that has 4 inputs and 4 outputs and has those causal relations can be decomposed into an extended circuit that looks like this, where the circles are unitary transformations. And you can see again that some of the wires have got indices on them, representing sort of direct sum and tensor factor combinations of smaller Hilbert spaces. It's an open question whether any multipartite unitary transformation admits a causally faithful decomposition like this. We have lots of examples where it does. We have a general result that says if there's at most 3 inputs and any number of outputs, then there's a causally faithful decomposition. Similarly, at most 3 outputs and any number of inputs. But it is an open question whether you can always find one in general. And I'll just say again, causally faithful here means that you've drawn an extended circuit like this, where there's a path from an input to an output if and only if the input causally influences the output. Okay, and now I'm just going to sort of draw everything together. And that'll be it, except for the speculative bit at the end. The above discussion about causally faithful circuit decompositions applies whether the unitary transformation being decomposed is associated with evolution just over 2 time steps, say T1 for the inputs and T2 for the outputs, or whether it's obtained from a multi-step process by stretching the wires. That is the big unitary transformation V that we had earlier, which represents a supermap corresponding to the process. So putting everything together, we get a picture that looks something like this. We might start off with a unitary process like this one, where some of the wires are broken. Those are the loci of interest, if you like, the ones for which we've decided to be interested in their causal relations. And so this one has some original inputs as well, lambda 1, lambda 2, and outputs mu1 and mu2. Starting with this diagram for this process with gaps in it, the broken wires, we stretch the wires. Okay, so there's that same process with wires stretched up to the top and bottom. There's a corresponding big unitary transformation V, which in this case would have A out, B out as its inputs, along with lambda 1, lambda 2, and A and B in as its outputs, along with mu1 and mu2. We can define the causal structure of V, that is, for each of the outputs of V, we can say what subset of inputs is it influenced by, and we can represent that structure just by drawing arrows. So just as an example, here's how it might look for some particular V. Then that causal structure, we might be able to draw a causally faithful extended circuit diagram. Now, if you can always do that, then we'll always be able to do it for V, but as I said, that's an open question. But actually, this one that I've drawn here, that's one that we do know how to draw an extended circuit diagram for. So any V with this causal structure can be written as an extended circuit that looks like this. And then by unstretching the wires, so by unstretching them, I mean we sort of bend them around again so that this A out bit here is again just on top of the A in bit, so it looks like a single wire with a gap. And B out here is just on top of the B in bit, so it just looks like a single wire with a gap. I can achieve that without changing this diagram in any way, except sort of bending wires a little bit, and we end up with this picture here, which is an extended circuit diagram for that original unitary process that I drew. And then that will have a causal structure determined by the causal structure of that unitary transformation V, which in the example I'm doing looks like this. And this picture, which is a unitary circuit diagram, is causally faithful in the sense that any node in this picture, if it's a direct cause of another node in this structure, then there is a path from our first node to our second node in this circuit that does not traverse any other nodes. If it traversed another node, it would be an indirect causal influence. Okay. I will finish off with those speculative, interpretive remarks. Okay, so we've seen already that there's a lot of sort of structure involved, and interesting structure at that when you start looking at causal relations amongst different points in unitary processes. And I hope that this will lead to a useful way of doing quantum causal modeling, much as classical causal modeling has turned out to be useful with all kinds of practical applications. But let's go in the direction of foundations instead. Let's just roll with the idea that causal structure is ontic, meaning out there in the world, independent of agents. So one way that could be true is if unitary evolution is in fact ontic, unitaries are ontic, in which case the causal structure of those unitaries is also ontic. It could also be something a bit weaker. Somehow the unitaries themselves are not ontic, but merely the causal structure of those unitaries. That could be a possibility. Okay, and rolling with this, let's suppose that in any quantum experiment in which we would normally say that a measurement device has a pointer, and each time you do it, the pointer goes left or right. Let's suppose the measurement device can be modeled entirely as a quantum system, as we ought to. Well, then let's suppose that we can describe the entire experiment as an overall unitary process, that in that process there are causal relations, as I've described them, and that you can represent that process then with an extended circuit diagram, which is causally faithful for that set of causal relations. And that diagram will typically have these indices on it, denoting sort of subspaces or orthogonal decompositions of Hilbert spaces. And the speculation is that facts that obtain on an individual trial, e.g. pointer went left, correspond to indices in that diagram taking definite values. Like an index I on that trial took the value 0 rather than the value 1 or whatever. This could be cashed out in various different ways. For example, you could try and turn it into a new kind of hidden variable theory, where the hidden variable is an assignment of definite values to each of those indices. And the theory itself would be defined by some way of ascribing a joint distribution over those index values for any given experiment, any given extended circuit. A slightly different way of cashing out the idea would be something more like Ravelli's relational QM. Somehow indices take definite values, but only relative to other systems, or even something Everett-like, wherein there's a world where I takes value 0 and a world where I takes value 1, a world where pointer went left and a world where pointer went right. But here would be that worlds are defined by the causal structure with indices and sort of distinguished by different values then of those indices. All right, and that's pretty much all I've got to say. I've got a blank slide here with conclusions written on it. I suppose in a way the conclusions are just to go right back to some of these questions at the beginning and say how each of these questions are answered by the account that I've given. But maybe rather than talk through all that now, I will simply stop and see if there's any questions or anything. Thanks.
Okay, thanks a lot. So we have one question.
Hi, this is maybe a very basic question, but when you did the causally faithful representation and you introduced the direct sum of terms indexed by I, what determines the cardinality of I there?
It's the unitary itself that you are decomposing. So where's a... So in any given particular example, these systems will all have definite dimensions, and it'll be some particular choice of unitary that you're decomposing.
But there isn't some simple relation between those dimensions.
Not really in general. I mean, for example, there exist tripartite unitaries, as I said, where you actually can draw a picture like this one here, where the eyes don't appear, which is kind of the same as saying there is an eye but it only has cardinality of 1. But then there'll be other choices of this tripartite unitary where I have to draw a picture with an eye, and the number of distinct values that eye needs to range over just varies depending on the unitary I'm decomposing. I mean, it never needs to vary over more than the dimension of the system.
One other quick question, your last slide in 4 with lambda and mu, is there a direction in that, in the diagrams where you had the circles, that kind of diagram, is there an implicit direction there from the bottom to the top, or?
So a nice thing here is that, I mean, I'm reading the figure from bottom to top, and I'm considering a unitary transformation that has inputs A1 to A4 and outputs B1 to B4. But you could also consider the inverse of that unitary transformation, and it would have inputs B1 to B4 and outputs A1 to A4. And there's this causal symmetry property I talked about. So you would get its causal structure just by inverting the arrows. And then that inverse unitary could be represented by a picture that looks like this, but read from top to bottom.
So actually, I also have a question about the slide you just had before with these different eyes and these tensor products. So maybe you said it in your conclusion, but I did not get it. Is there a way to maybe physically interpret what this formula means? Do you have, I don't know, selection rules, stuff like this?
With the formula here, I mean,
yes. So if I have, for instance, let's say I equals 0 and 1, what does it mean physically? Can I say something?
I guess so. Well, is this in connection with the speculation I was making, or are we not worrying about that for now, and you're just asking me about the diagrams?
Well, just in the diagrams, yes. If you have such a decomposition with, let's say, two different eyes, how can I associate let's say, can I associate a concrete physical interpretation of the way I decompose the unitary?
I guess let me say a little more in case it helps. One thing that I didn't explain very much is what this VI here is. It's a gate, I said it's a unitary transformation. But you have to give an interpretation, a sort of semantics for this type of diagram, in which you see this gate. It crosses this wire here. One of its inputs is this wire, and one of its inputs is this wire here with an eye on it. But it doesn't cross this wire here, which also has an eye on it. So, and I've written VI inside this box. So what does that mean? It means that there's a unitary transformation there, V, which is really a unitary transformation on both of A1, A2. It's just that that unitary transformation is block diagonal with respect to the decomposition indicated by I. And inside each block, that unitary transformation V only acts on this term here, the left term, the one associated with this wire, and its identity on the right term here. So physically, you could say it's telling us something about the way this A2 system is interacting with the A1 and the A3 systems. It's saying that the A2 Hilbert space decomposes into a direct sum of orthogonal subspaces. But then inside each of those orthogonal subspaces, you've got this factorization into 2 bits. And A1 only interacts with one of those bits, and A3 only interacts with the other one of those bits. I think that's the best I can say in this sort of quite general setting. In actual physical examples, of course, we wouldn't just be talking about abstract systems, but sort of ions or whatever, and these unitaries would actually correspond to specific interactions, and therefore we could say things about them.
Okay, and you can say something which is related to what you just said at a quite high level.
Yeah.
Okay, so I think sorry.
Thanks for the lovely talk, John. I'm just interested in the distinction between the causal influence and causal signaling that you made at the start. Mm-hmm. So the two examples that you gave, the C0 gate for the quantum case and the example for the classical case. So the way I would think of it is, in both cases, you can actually uncover what's going on as long as you have apt control. So once you can get in and vary those parameters, you can see what the kind of true or what the causal story is that's underlying that fine tuning. You can kind of see why it's fine tuned. So in that instance, it seems like you do kind of need signaling to make that distinction. And if you want to posit that they are actually, in fact, different things, then it would seem that you ought not to be able to discover, or the physical situation through interventions. And if that's the case, then you're kind of positing a causal influence that you can never know, you can never discover. So I just am a bit confused about why there is that distinction.
So I think I just agree with you, actually. So I don't think there's a disagreement between us there. So with this classical example here, I suppose really I was tilting at a certain attitude you see that one finds in sort of lots of papers, specifically from sort of in the quantum information community, where people talk a good deal about causal this and causal that, but pretty much just define causal influence as signaling through a general channel, just in an operational kind of way. And when you do that, you don't sort of bring out this distinction between there being no causal influence and there being signaling washed out by fine-tuning. So in this example here, that the point is supposed to be that there is causal influence from X to Z. And for a function, you can understand that very easily. It just means that in the function, Z does have some functional dependence on X, as well as on lambda in this example. And of course, that is equivalent to saying that for at least some distributions over lambda, you can signal from X to Z. So we can say that causal influence is signaling here if we want to. But only once you've got the full picture, which involves the function f and the variable lambda.
So I think we also have questions online. Okay. Maybe the people online can directly ask them.
Can I ask a question?
Please do on.
Sure. So John, thanks for the talk. That was interesting. So one question is, you start out with an unitary without with some circuit that without the broken wires, right? And then at some point you break some wires and stretch them out. And then you ask, well, can I give a causally faithful decomposition of the resulting unitary after stretching the wires? And then in some cases you find you can. Is there a guarantee? But then you could choose instead to break some other wires rather than the ones you picked up at first. And then you would get some other unitary between different Hilbert spaces, which maybe would get a different causally faithful graph with a different kind of decomposition. Is there a guarantee that there's some consistency between the graphs if you choose to break this unitary in different ways? Or if you start by breaking one way and they won't get one graph, but now what if I now keep breaking some other arrows? Is there some guarantee that there's going to be a consistency between the graphs? Or could it be that you get completely different decomposition that you can't match to somehow being part of the same graph?
I mean, I think there'll be a guarantee of as much consistency as one should require.
Right.
So any causal talk at all, and this is true in both the quantum and the classical cases, is relative to how we've decided to carve up the world into different bits. And which of those bits have we decided to be particularly interested in and which are we ignoring? So to even talk about unitaries with multiple inputs, you've made a decision about how to factor some big system into multiple inputs. Mm-hmm. But all of this is true in any kind of causal stories, as I said, even classically as well. Like if I'm considering a coin tossed on Earth and another coin tossed on Mars, I might judge that they're independent and assign a probability distribution that factorizes, sort of based on Reichenbach's principle or something. That's what I do, and might have that might form the basis of some whole causal story. Of course, if I decide to do something weird and decide that one of my systems of interest is the parity of those two coins, and the other system, I don't know, just the Earth coin on its own, like just factor the whole thing completely differently in some weird way, you're going to end up with just a different causal story. And it's not just how to factor things, it's the questions of coarse graining come into it as well. And which presumably are not considering all of the universe at once. Most of the time I'm doing causal reasoning, so there's been a decision about which bits to ignore. So I think the right way to see it is that any kind of causal talk is relative to a particular way of carving up the world and deciding what we're interested in. And there can even be a sort of anthropocentric element there, you know, how we've decided to carve things up might be relative to our own interests. But I think with that proviso, it's still right to see causal relations as ontic. Just because it's relative to our interests, it doesn't make everything sort of epistemic in the way that probabilities are. So you're quite right in a way. You'll end up with different sorts of stories depending on where you put the gaps in your circuit. Or even if you factored things differently and drew a different circuit. But I think that's to be expected.
Okay, so we are over time. I think there is still a question online, but I propose that like you discuss it online. We'll make a very short break, and I don't know how much time we have. Just a glass of water time. Okay, thanks a lot.